Imagine chemistry not in a static vat, but in perpetual high-speed motion. This is a plug-flow reactor, or PFR. It is a tubular system engineered to operate under strict steady-state conditions, where the input of raw materials and the output of products never stop. The defining conceptual feature of this architecture is the plug. As reactants enter the tube, the fluid dynamic model treats them as discrete cohesive disks, or plugs, pushing forward in a continuous stream. The central physical requirement here is that every isolated fluid element must maintain the exact same velocity. Because of this uniform forward momentum, the fluid cannot mix backward along the axis of the tube. In a standard batch reactor, you observe a chemical reaction progress over time within a fixed space. In a PFR, that timeline is stretched out physically. The chemical composition changes as a direct function of distance traveled. By completely eliminating axial backmixing, process engineers can map the exact duration of a chemical reaction directly onto the physical length of a continuous pipe. This animated design equation defines that spatial mapping. It calculates the integral of the concentration changes across the entire internal volume of the reactor. The output of that calculation is tau, the precise residence time required for a specific fluid plug to complete its journey from the inlet point to the final outlet. For a standard first-order reaction, the rate is determined by multiplying the concentration by the kinetic rate constant K. This constant serves as the mathematical engine driving the progressive chemical transition as the plug moves forward. As the isolated plug advances down the spatial axis, the initial inlet concentration systematically drops as the raw reactants are consumed by the process. While the flow strictly prevents any mixing backward or forward, the molecules within each individual plug are constantly mixing radially. This internal churn guarantees a uniform chemical conversion from the center of the pipe all the way out to the physical walls. Maximizing conversion efficiency requires taking this abstract calculus and building it into a rigidly controlled physical architecture. Looking at this technical schematic, the continuous pathway of the tubular body provides the heavy metal enclosure required to execute our theoretical flow. At the start of the system, the feed inlet must introduce reactants at an exquisitely controlled rate. Any surge or fluctuation in intake pressure could destroy the laminar flow necessary to maintain the discrete plug structure. Wrapping entirely around the main tube is a heating and cooling jacket. This mechanism manages the internal reaction temperature, granting engineers direct physical leverage over that kinetic rate constant. Mounted along the tube exterior, temperature and pressure sensors continuously monitor the internal environment. These real-time data points ensure the strict, steady-state conditions required by the equation are maintained without interruption. Finally, the product outlet must smoothly and continuously extract the reacted mixture. If this extraction creates sudden pressure backwaves, it will immediately disrupt the upstream flow dynamics. Every physical gauge, jacket, and valve mounted to this system exists solely to protect the mathematical ideal of the continuous flow from the thermal and dynamic chaos of a real-world manufacturing floor. Inside the tube, this diagram highlights the system's defining visual characteristic, the chemical concentration visibly varying along the length of the flow path without any backward contamination. Because the highly concentrated raw feed at the front is never diluted by the reacted products further down the line, this spatial gradient achieves unparalleled conversion efficiency per unit of volume compared to mixed systems. The physical geometry itself yields immediate engineering advantages. The long, narrow shape provides a high surface area to volume ratio, enabling highly efficient heat transfer between the interior reacting fluid and the external jacket. Operating continuously at a steady state guarantees constant output. This bypasses the massive productivity losses associated with the heating, cooling, emptying, and cleaning phases required in sequential batch processing. When it is time to scale up industrial capacity, engineers rarely have to invent new geometry. Output can typically be increased simply by extending the length of the physical tube or by routing multiple identical pipes in parallel. These integrated physical advantages make the PFR an exceptionally powerful tool for continuous production, provided the chemistry behaves perfectly. When that flowing stream suddenly thickens or crystallizes, the ideal physical model rapidly collapses. This reveals the system's primary weakness. Plug flow reactors are notoriously difficult to operate when handling solid-forming reactions that can easily pile up and obstruct the continuous narrow pathway. Highly viscous reactions pose a similar threat. If thick fluid adheres to the reactor walls while the center continues to move quickly, the entire plug assumption breaks down, resulting in wildly unpredictable residence times for different parts of the mixture. The steady-state requirement itself is a mechanical vulnerability. Pushing fluid forward with absolute, unchanging consistency demands extremely precise and often highly expensive continuous flow control pumping hardware. Multi-phase reactions, such as complex gas-liquid mixtures, further complicate the internal design. Running these requires specialized internal baffles and structures just to prevent the phases from separating as they travel. The continuous tubular reactor is a highly precise architectural instrument. Its efficiency drops to zero the moment the physical properties of the fluid deviate from the mathematical boundary conditions. Moving out of the isolated theoretical model and into a large-scale manufacturing environment, we find massive, interconnected arrays of continuous systems running in parallel. In pharmaceutical manufacturing, these systems drive the continuous synthesis of complex active pharmaceutical ingredients and highly sensitive chemical intermediates. They are uniquely necessary for volatile, highly exothermic processes like hydrogenation and oxidation. Here, the continuous flow and superior heat management aggressively prevent the possibility of thermal runaway. In precise polymerization and esterification, the strict spatial control over residence time dictates the precise molecular length of the final polymer chains. Modern facilities are now engineering specialized PFRs explicitly designed to force continuous crystallization under strictly controlled flow conditions, overcoming the reactor's historical limitations with solid-forming chemistry. Continuous flow architectures have shifted heavy pharmacology away from slow, localized batch chemistry toward rapid, highly scalable continuous manufacturing. As this chart demonstrates, the continuous output of a steady-state PFR drastically outpaces the inherent downtime of standard batch operations. The power of the system lies entirely in marrying that high conversion efficiency with absolute mathematical control over the reaction kinetics. By enforcing a completely uniform residence time for the reacting fluids, chemical engineers can guarantee the highly consistent product quality required to meet strict pharmaceutical GMP compliance. The plug flow reactor remains the ultimate physical manifestation of spatial geometry directing the precise mechanics of chemical conversion. To master the mechanics of continuous manufacturing and explore more deep dive masterclasses on process engineering, subscribe to the channel.